Hello, thanks for coming to the presentation. The title of this project is Calorie Estimation from 2D Photo, Physics-Informed Portion Estimation for Automated Calorie Tracking. There are many apps taking photo of food and estimate calorie from that picture. The challenge is still in inaccuracy of that estimation. So I focused on um, improve it, and in particular on in the volume estimation. Um, I focus on the um, depth estimation, meaning the distance from land to the food, and try to improve that by improving algorithm, and that as the improvement will improve the volume and eventually the calorie calculation. Here is the diagram that gives the overall structure of this model. So the RGB image is 5,000 sample that publicly available by created by Google Lab, and those are different kinds of food that took a picture in the lab kind of environment. And using those data, I set up ResNet 50 as an encoder. And here then I include two heads. First head is a depth estimation, and the second head is a food classifier. So from head one, depth estimation, estimate the volume, and then head two is food classifier, and it's looking it has a lookup to the density, and so multiply that together, give you volume, multiply density, and it gives you the calorie. So that's the overall. These projects is focusing on the depth estimations, and uh, by the base case is the loss function using the mean square error loss, and the improvement is by adding the physically informed neural network constraint, so it's called PINN constraint that penalize the surface curvature to enforce the smooth and gravity consistent geometry. So that's the major focus in the project, and the result in the depth estimation is here. I'm comparing the train mean absolute percentage error and test set made. And first here, baseline case based on mean square error um, is showing 5.36% in the depth estimation, and test set showing 5.77%. With the added constraint, it gives significantly improve MAPE with 0.71%, and test MAPE is 0.89%. So improvement is seven multiplier, the 7x and 6.5x. Based on these, the physics informed constraint successfully enforce that the realistic surface to the non-rigid food, achieving quite improvements. And the technique that I use for the overfitting prevention is I use photometric augmentation by adding plus minus 20% brightness and contrast to the randomly select image, so that to make sure that model um, estimate from geometry, not from lighting. And I also use dropout 50%, and I can see that the resulting in the gap between train errors and the test error is within 1% point, 1% precisely 0.18% percent point. Um, I also did the stress testing. On your right here is the pictures of stress testing that I did. I again used the same technique of the adding the photometric augmentation to the data. This time is more extreme, so that zero point 0.4 to darken the light and 1.6 to brighten the sample. And you can see here, the first case, the first picture is an original. Then the second one in the middle is the darkened one, and the third one is the bright one. I see that the made vary from 0.42% to 0.76%. So the original case was 0.42%, dark one was 0.48, and the bright one is 0.76%. And I think that's a relatively stable error without any spike. So that's the kind of prove the robustness of this model. I had to specifically to calculate the calorie by implementing end-to-end. And there was a benchmark in the reference paper, in state of art, a benchmark is about 14% error right now. However, I was not able to do better than that because the major issue was the segmentation. Right now, the segmentation that I use is only for the single segmentation, whereas I will need to implement mask to former semantic segmentation to basically isolate the food from the plate background, and also within when there are several different kind of food, then I need to isolate them too. So that's a future work. And during the testing, I also try to test for the scale ambiguity by giving a distance from the food by like different distances, from 0.3 meter to 2 meter. And I creatively use 3D data in this. And I can see that the error reduction was quite sizable. However, there will be more to do with the real world testing by, nowadays like using LiDAR or AR4 from the phone. So that's another thing. The future work still remains in retrain classification head to the more of the realistic Casperia data. And so that's beyond what's been used in the sample. So those are three future work. I think overall though, in terms of the depth estimation that where this project is focused on have show great improvement by adding physical informed constraint into the algorithm, and by as supported by lower mean absolute percentage error in the algorithm result. All right, that's the presentation. Thank you. Bye.